All right, my friends. So, exam due Friday.
Yeah.
Let's stick with that. Exams due Friday. I'll be in my office. If you can get it to me before like noon, that would be ideal. I might be hanging around later for something I may go to. We'll see. See if I can stand it. Is there any questions I can answer before I get into some integration? I don't want to spend too long, certainly not going to spend a substantial portion of class on answering questions, but I'm happy to answer them.
I have one.
Yeah.
Okay, so on. I'm flipping.
Are we looking at the exam? Is that what you're?
Yeah.
Okay.
Okay, so on 3 point, or on number 3, so part, the original curve C for E to IT is the half circle centered at 1 over radius 3. And then 1 over 3 E to IT is, if I understood that correctly, so when Grace and I were working on it, is it not just the bottom half of that circle?
Kind of,
Kind of, okay.
but I'm not, you should keep an eye on the orientation of it as well.
Okay.
Actually, it might, I don't know, maybe it is the bottom half.
I,
Because when you do this, so you've got this,
yeah,
you want to rewrite that, you want to multiply by the conjugate.
oh, cause you're just taking the free and using it as a.
Yeah. So this is the curve you're going to sketch out.
Okay,
And I'm pretty sure it moves the other direction. So I think the original moves clockwise
Yeah.
or counterclockwise,
Uh-huh.
and then this one will move counterclockwise.
yeah, okay, so we weren't completely wrong on that.
No, the
Great.
shape is the bottom half, absolutely. It's just the orientation is different.
Okay, so then when I got to part D, it said that 1 is a line segment. And I think it's talking about part C where it's 1 plus E to the IT,
Yes.
although that's still a circle.
But
It's
the
just like
transformation
centered.
of
After the transformation. So we've got two things, right? We've got this little half a circle, and then I ask you to do something like this, right? And we're gonna, am I getting the problem right? Is this, or am I doing a different problem?
There.
Can I see, which one was it?
Yeah.
Sorry. It was 3.
So, yeah, A.
Yeah. I got it right.
Yeah.
Yeah, so in C, this is your original curve, and I'm honestly not sure if we traverse the whole of it or not. I don't know what I said the parameter
It
is.
says 0 to pi.
Oh, just 0 to pi. So does that actually just the top half of it?
It should be, yeah.
Oh, okay.
But it,
Then that's much less interesting than I was hoping. I should have done 0 to 2 pi. Yes, ma'am.
I had a theory that, because when I was drawing the line, I was getting an infinity at pi. So I was wondering if because you said the infinity was getting mapped to 0, 0 on that one. So,
Well, 0 is getting mapped to infinity. So this is the whole circle. So actually, I think it actually is going to work out the way I wanted it to. So this circle here, if you do the 1 over z to it, you get a new circle, right? This original one was radius 3,
yeah.
and then the image circle is radius 1/3, moving in a different moving in
Uh-huh. Yeah, just
the opposite direction.
Uh-huh.
So that circle went to a circle. But if I take this circle and run it under 1 over z, some key points are going to change. So let's see. So this is 2 up here. So that's going to go to 1/2. Excuse me, that's 2i. What am I talking about? That's going to go to negative 1/2 i.
yeah.
Yeah, so negative I over 2 down here. So we've got a going there and a going here. this 0, we're never gonna actually make it to infinity on the output if we're just doing the top half, which it sounds like we are. But if I did the whole circle, this infinity here, or the 0, would go to infinity. So this 0 right here would go to infinity. Notice there's 2 different ways to get there, and that's just the 2 ends of the line. So it's kind of like these 2 parts of the circle that are approaching 0 under 1/z become the ends of the line moving out toward infinity.
That is not what I have. I might be totally wrong on that.
I don't think you are. I already looked at what you're doing. It was completely right. I'm pretty sure I looked at what you're doing. Maybe I'm thinking of something else, Lavina.
No, you did look at what I was doing.
I didn't look at what you're doing, okay.
Okay, and I did not know 3 had a D. Damn it.
Okay, there you go. We got some stuff to do. So this is t equals 0. This is t equals pi. T equals 0 is just the point 1 plus I. So what's 1 over 1 plus I? That's going to give you where this thing goes. And I'm pretty sure it's like down here or something like that. It's like 1/2 minus 1/2 I or something like that. I don't quite remember. But it lines up with this thing, and so what you end up with is a line segment.
Oh, that's where
This
that,
turns into a line segment.
that's where that came from.
Yes.
Okay.
Okay.
And that's because the full circle includes infinity, and when you have a circle that includes when you have a circle that includes 0 and you do this to it, that 0 goes to infinity and it turns into a line.
Okay.
If I have a line, I'll be right there in a second, Lavina. If I have a line and I do 1/z to it, that's a circle that has a point at infinity, so that point will move to 0 at that point.
Okay.
Lavina, yes ma'am.
For C, we have 1 plus e to the IT.
Yeah.
So
Yes.
wouldn't the center...
Oh, yes, I did this ass backwards, yes ma'am. The circle, I did this, and I did this the other day when somebody else was talking to me about it too.
Yeah.
Is that not what we have?
We have this, but you have this, so you're right, Lavina, it's actually this circle here.
Yeah, that's what I was saying. 'Cause
Yes, ma'am.
That's
Oh,
why I
okay.
had infinity at pi.
You're right, then that is 100% correct.
Okay.
Okay.
That's what I was thinking also, because with transformations and everything, since we had infinity at pi, that meant like that line was going to, like that curve was going to infinity over there.
Yes, ma'am.
And so that curve was kind of translating into that line that's going straight down, right?
Effective, yes.
Damn it, I did not have that recorded. Because I'm gonna forget what
Well, it's
I
on,
said.
you can look at the recording and
Okay.
listen to what you said and write it down.
I love that.
Does the mic pick up what you say? Or
So
not?
I'm talking with my big girl voice.
Yeah, she is. Look at her go.
It's not the brook babbling sounds, it's just like, what was that?
No,
You
I said-
recorded last time.
No, I
was doing your voice.
I know, I recorded that part and I sent it to Sydney and I'm like, you guys are not gonna let me live this down my
Absolutely not, no ma'am.
Other questions on the exam? No? Okay, and then part D is just like, part D is where I ask what's going on here, is that right, or is
Oh,
that?
yeah, I
And
did
why
that.
is it the way?
And why is it going on? So this circle here doesn't involve 0, so when I reciprocate it, it should not involve infinity. That means it stays a circle. This circle here does involve 0, so when I take the reciprocal, that 0 will go to infinity and this will become a line. So it's really just like simple. I'm not looking for anything heavy there. You don't have to write an opus, like a couple of lines, maybe a picture of the Riemann sphere if you like. It's all good.
I was going crazy.
All right, and you're not going crazy more than the average. And I won't give an assignment unless anybody wants one. So I won't give an assignment except for those who request it. And I'll have to like come up with that. But let me know. I think there's some in here who probably are like, yeah, give me an assignment.
Yeah, we know who that's that is.
You're okay?
No.
This is like home stretch. There's two big things I really want to talk about the rest of the semester. One is integration, and the second is series. So integration is going to turn out to be pretty different than what you're used to. In fact, it's going to turn out to be very elegant and shockingly beautiful. And it's going to be intertwined with series. You're used to this kind of series, Taylor and Maclaurin's. What's the difference? Do you remember?
Taylor is centered at 0.
Yeah, exactly. Taylor's series were centered at 0. Maclaurin's were arbitrary centers. So every Taylor series is a Maclaurin series. We're going to be looking at kind of name just Laurent series. And this is where we can have negative powers. So you can, in a Laurent series, you could have a series that looked like this. Put your favorite number on top of here. So a Laurent series can actually be doubly infinite with negative powers as well. This is going to be really cool, really fun. A lot of the ideas are very similar, but there's also some different ideas in here. So let's get going on to integration. All right, so there's a great quote on page 71 that I wanted to read together. So on page 71, the integration intro quote says, "If things are nice, there's probably a good reason why they are nice. If you do not know at least one reason for this good fortune, you still have work to do." Richard Askey, whoever that is, but man, that's a great math quote. We're gonna see some beautiful stuff here. We want to try to gain some sense of why it's so beautiful. So first off, let's start off chill. Let's just do an example. Let's say I've got a function h, and it maps from a subset of the reals. So a closed interval in the reals into the complex plane. So notice the input here is not a complex number, but the output is a complex number. So, for example, h of t would look something like this. It's got some real part plus some I times an imaginary part. Got it. And these are just regular old real functions. So for example, and this is the example we're going to use, so I'll say here, let h of t equal 2t plus 1 over t times I. That's a t there. And this function is defined everywhere except where t is 0, but let's be really precise. Let's say h maps the closed interval 1 to e into the reals. So I'm just specifying the domain here because I want to think about this. Consider the integral as t moves from 1 to e of h of t dt. So just a good old integral. This is like Calc 1. Nothing freaky here, nothing weird going on. How would you do this in Calc 1? Well, you take the antiderivative of this, plug in the limits, and subtract. Straightforward. But here it's a little bit weirder because when I replace e with its definition, it's going to be 2t plus 1 over ti dt. Good news. It's still Calc 1. Even though there's an I in it, that I is just a constant. So I'm going to break this apart. So this is integral 1 to e of 2t dt, the real part, plus I, the imaginary part, 1 to e, 1 over t dt. Look at how nice that is. I just pull the I part out and keep that in front, keep track of that, and then do the rest of this calculus. So what's the antiderivative of t squared? and antiderivative? Oh, sorry, I gave the answer to the shit. Yes, you are correct, my friends. It is t squared. What is the antiderivative of 1 over t?
Natural log of t.
And we can, sometimes we put that absolute value on there if we want it. I got this. So when I work this all through, this is just e squared minus 1. I do that part. Plus I, what is the natural log of e? 1. What's the natural log of 1?
0.
I love that. I love that you know that. So this is my answer. Now we can't like say, oh, this is the area under this curve, because the curve is nonsensical in this sense. It's just some weird function. This is actually just a line in real, in the complex plane. So if we kind of take a look at this, this is our input here. And I'm saying our input is just this curve from 1 to e, just that line segment on the real axis. And I run that over here, and I've got a whole variety of things, right? I've got this changing and this changing. It looks like this part grows as t moves from 1 to 2, but this part decreases as t moves from 1 to 2. And we would actually see something like this over here as the curve. So then this is h of that input. And we're integrating that, whatever that means. It doesn't mean a whole lot at this point. So here's the summary really quick. This is our easy case. If I want to find an integral, and I only have one input variable, and it's a real variable. So if I have h real of t plus h imaginary part of t with an I in front, I just do the parts separate. And it becomes calc 1. Easy. So you just have to go review calc 1 to do that. That shouldn't be super taxing, and it's certainly not mind-blowing any more than it was. Well, hopefully it's slightly less mind-blowing than the first time you saw it. So that's our easy case, but let's make things a little more interesting. I want to put meaning to this expression. So what does integral over some curve c of a function f of z dz mean? So this c is a curve in the complex plane, and it has to be given by some parameterization. So the parameterization I'm just going to assume is that c is given by gamma of t, I put a colon here, and that t goes from a to b. So now I still have that interval, that t interval, like I kind of had here, but it's first passing into a curve. So let's take a look at what we got here. So here's complex plane, here's c. And let's say it's oriented like this. So this is gamma of A, this is gamma of B, and our flow runs from left to right, or from lesser t to greater t. And I'm going to take that, and I've got this function f, and it does something to this curve. So this f does something weird to that curve. So let's say this is f of c over here. And what we're interested in is understanding what it means to integrate that function f, whatever this is that's doing this transformation, along this curve. Okay. Is there a question, Noah?
No, I'm just thinking.
Thinking, yeah. That was a thinking sound for sure. All right, I'm going to give you the formula, and I'm going to explain the formula after. Now, book doesn't really get into why the formula is so, and I'm going to give a very heuristic, loose argument, but I think it's going to make sense. So, this integral, C, and your book actually writes it like this, our book writes it like this, they don't put a variable, but we'll put in a variable. And so both these notations are totally legit. This is just like, hey, use your favorite, you like Z's or you like W's? What do you want? Put it in there. Here I'm saying, I like Z's. And so to do this, we're gonna integrate from across the parameter range. We're gonna take F and plug gamma into F. So we're feeding, so here's the output, gamma right here, right? And there's even like this real line back here, A to B, and that's just R. And when I run that through gamma, I get this, that's under gamma. And I'm gonna feed that into F. So using functional composition, and then I have phi, and I won't use dot because Noah doesn't like it, so I'll put phi prime of t.
Thank you.
You're welcome. It's the small things that matter.
Yeah, I appreciate it.
I'm happy to make you happy or less, or not irritated by the dot. So why is this so? Let's think about this. So here's a rough argument as to why. So let's be naive about this. Integral C of f of z dz means I'm going to take this curve C here, cut it up into pieces, right? This integration is all about cutting things up into pieces. So the first thing I'm going to do is take that curve C, let me try to replicate it again, and I'm going to cut it up into n pieces. So let's cut C into n pieces, and they don't have to be equal. That's fine. We'll call this gamma 0, gamma 1, gamma 2, gamma 3, on up to gamma sub n. So the partition looks like this. Is going to bless you or something. Maybe not the right word. We've got gamma 0 less than gamma 1 less than up through gamma sub n. And this equals gamma of A. That's the left point. And this equals gamma of B, the right point. So this is gamma of A. This is gamma of B. And then I'm going to evaluate F at either a point in any of these intervals, or maybe the left end point of each of these or the right end point. But remember how this integral works. I'm going to write something super rough here. So this is equal to the sum of F evaluated at a point in each subinterval of C. So we're taking C and we're cutting it into these little pieces, times the length of that piece. And that's what an integral is. You just sample in each of these little pieces, multiply by the length of each of those pieces, and we're good to go. And I'm putting length in quotes because it's not going to be precisely length, but it's going to feel like it. So this thing here is going to equal the sum, and we're not going to put indices here, we're just going to put the stuff we're summing. So I've got F evaluated at gamma of sum, how about we just say this, we'll say gamma star sub I. And this is a point in the ith sub-interval of gamma. And then here, I'm going to have the changing gamma.
What's that at the top? Like of the, no, like of the
Sorry.
thing that you just wrote, like the thing.
That's a star, sorry. Is that what you're asking?
Yeah.
Yes. So that's a little asterisk there. So what do I mean by gamma star? Well, gamma star, let's actually draw a little picture here. If this is gamma, if this is curve C that's given by gamma, and this is gamma 2, and this is gamma 3, then gamma 2 star is just one of the points inside there. Does that make sense? It's kind of like grabbing any point I want there. And sometimes you use the left endpoint rule in Calc 1, or the right endpoint rule, or the midpoint, all sorts of ways to do that. Good news is it doesn't matter, we get to the same place. So we got this. Well, let's pull that back, because these gamma, each of these gammas, each of these cuts comes from a place in the subinterval. So gamma 0 comes from here, that goes to gamma 0. There's some other T1 that goes to gamma 1. There's some T2 that goes to gamma 2, and so on. So I'm going to pull back to the T space that gets me these little markers that I put on here. This is T0, T1 gets me here, at time 2 I'm here, at time 3 I'm here. So this is equal to the sum of f of gamma of t sub I, and I'm going to move the star here, so I'm picking some t, the t that corresponds to this point on gamma. And here I'm going to put delta gamma again. And let's put gamma sub I here, just because those, what this means, what does that mean? This is gamma I minus gamma I minus 1. So it's literally just the difference in these two things. You might want to just put, here's delta gamma 2. It's this line segment right here. Here's delta gamma 3. It's this line segment right here. Almost done. Almost done. So now I'm going to do something tricky. I'm going to do something you've seen many times in your math life. I'm going to replace gamma or delta gamma I with delta gamma I divided by delta t sub I. And I'm going to multiply by delta t sub I. So nothing fancy yet, but what is this kind of starting to feel like? If delta t was really small, what would this? Yeah, it's a derivative, right? This is how we get to derivatives. So this thing here, as the delta t's get smaller, this whole thing approaches, given that f is nice and gamma is nice, and it always will be for us. What do I mean by nice? Continuous. That's all we need. Nothing flying off to infinity, no craziness like that. So as these delta t's get smaller, this approaches the integral of f of gamma of t. This is the derivative at that t. And then this part just goes to dt. And this parameter range on the t's was from a to b. So that's a rough thinking through of how this becomes this. And this is how our work gets done for a while. And then it's going to get a lot easier. We're going to suffer. As with every math, we suffer. And then things get better. First we walk up the mountain, then we learned there was actually a lift on the other side of the mountain that we could have taken up.
Oh yeah. I'm remembering calculus where like integrate all these things with like the extended version of the derivative. Or
Did they have you do, who's your prof?
I was in high school.
I was in high school.
But they're like, yeah, for the first year, you're like, you couldn't use any rules. You had to do it all by hand.
Oh my God,
But
that's hardcore for high school. I'm
well,
impressed.
they wanted to make sure you knew it. And then once you had done the basic ones, they're like, okay, and now you can use the treaty rules. But it took, you had to do it. You do it without the left choice.
You earn that. You earn the right
Yeah.
to use the power rule. It's a hard one, right? Alrighty, let's do a nice integral here. Let's see here. Oh, why not? Hey, let's have fun immediately. Yeah. Okay, you ready? Yeah.
You didn't sound ready to be done.
Oh, we're gonna like this. I just can't wait to do this. I don't have the curve yet, so let's put here the curve C, and then I give you C. And C is going to be e to the it. T runs from 0 to 2 pi. What is that? Circle, centered at the origin. So here's our C. Is it clockwise or counterclockwise?
Yeah, counterclockwise.
CCW, yeah, right, we start here and then as T evolves, we just move counterclockwise.
Okay.
Sound good?
Wouldn't this just be 0?
We'll see. Who
Okay.
can say? I guess I can say because I know the answer, but
Yeah.
it's not 0.
It's not 0.
It's not 0.
The ending and
I
starting
got
points are
you,
the
Noah.
same.
I knew you would think that. I had a sense you would think that was good. I felt right. I tried. Oh, okay. All right. So let's do this. So gamma of t is the curve definition, and that's e to the it. What's gamma prime of t? What's the derivative of that?
E to the IT.
It is very close.
Over T here was
So it's
I E to the IT.
yes.
Like that.
So e to the it times the derivative of the exponent, which is just that. Yeah? Cool. So let's go to our definition. Here, so this is equal to the parameter range, 0 to 2 pi, 1 over the function. Now I'm replacing z with the gamma definition, because this is what it looks like for us. Times 1 e to the it. So this is the gamma prime of t. This right here is 1 over gamma of t. And then dt. Can you finish that up for me? Please? Some nice things happen. Hell yes. Some super nice shit happens.
Oh, yeah, I think it, yeah.
Well, it isn't 0.
You're good. I'm glad I got that right, because it would have been pretty confidence shattering if I hadn't. Yeah.
The hubris.
Yes, the hubris. Yes, the hubris. What'd you get?
2 pi to the I? Or
2
2
pi.
pi I, not
2 pi I?
Yeah,
We
2
get
pi
2 pi I? Let's do this together. Yay! They cancel. It's actually just this. And that is, you can pull the I out in front or whatever you want to do. It's IT. T runs from 0 to 2 pi. Plug in the 2 pi. Usually we write this 2 pi I. Put that I at the end. So it's not 0. Let's do another one. What is this integral? Same curve. Don't say it out loud. Let's work it. I'm going to come around.
You said same.
Same curve, yeah. So our C is this unit circle, precisely described here. don't get that nice canceling, right? That's not gonna happen this time. But still, it's just an E thing. So we just have to know how to handle an E thing. What goes in front when I take the antiderivative? 1 over 2i, yes ma'am. Exactly.
I always like switched up.
You rocked that one. How you feeling about this one, Noah? Is this one a little more like what you were expecting?
Yeah, it is.
Indeed. So the i's cancel, and then we get e to the 4 pi I minus e to the 0 I if we want. Now I have to go to Euler's identity. That e to the whatever I is cos of that, so I sine of that. And so this is going to be 1/2 cos of 4 pi I sine of 4 pi. This is just 1. And this is certainly just 1. We don't even need complex analysis for that. I'm going to get a 0. So these two answers, this 2 pi I and the 0, you're going to become very good friends with these answers. You're going to see these answers a lot. At this point in complex analysis, you don't know what the integral is. 0 is a good guess. 2 pi I is your second best guess. And I'm kind of joking, but I'm kind of not at the same time. What is the difference? What is the difference in these two? What's going on here versus here that just seems like just different? Is this function, is this an entire function? Is Z entire?
Yes.
Differentiable everywhere, right? Definitely differentiable. What's the derivative?
1.
1, cool. Is this continuous? If the input moves a little, does the output move a little? It better. It's the same damn thing. The input is the output. So if the input moves a little, the output moves the same amount exactly. Is this entire? Where is it messed up? Messed up at 0. How does 0 relate to that curve? Smack dab inside of it. I'm just making some notes here of some things that we'll care about as we move forward. But notice this has a singularity inside the curve. That does not. Let's try another one. So I would like you to please do, I'm going to give you a new curve, C, and we're going to do 1 over Z minus W dz. Let me make sure I'm doing that right. So got this set up. Yep. So W is a complex number, and right now I'm asking you to interpret some things here. So C is given by W plus RE to the IT. R is a positive number. T runs from 0 to 2 pi. Please do this integral. W is a constant, so Z is your variable. All differentiation will take place with respect to Z. W is just a placeholder. And there's like a couple things here. What is this? So what is C? What does it look like? And then what is this? 2 questions. wanna try this one, Lou? Okay, keep you busy. I want you busy, I don't want you bored. How's it going? Uh-oh. Yeah, exactly. So literally replace the Z with that curve definition. W's a constant.
So sit on top.
Yeah, W's just a constant. Yeah. Does that help?
Yeah.
Okay, cool. Yeah, oh, you're rocking it. That's how you do it. You just start writing stuff. And it starts to unfold. Yeah, oh, that's so nice. That's a nice whiteboard. What is that called? OneNote. Oh, that's just like resident on Apple stuff, right?
Yeah, like that's what I do, like, oh my.
I'll have to try that.
And then
No,
you can
it's
also
very
do-
nice. Oh, okay, I gotta start doing that. That should be on my iPad, right? Should, or I can get
You
it
can
from my.
get it, it's just a Microsoft thing,
Okay,
yeah.
alright, I'll look into that. How's it going, Olivia? Feeling okay about this?
Yeah.
Okay, okay,
Um,
okay, yeah, that looks good, that looks, yes. How you doing? Yes, but we're missing something here. So the gamma prime does not go down here, so I literally replaced that z with this expression. Yeah, and then it's times that I e to the, yes. Yep, indeed, indeed, you're doing the squared version, awesome, awesome. Oh, good. Yes, nice. It looks good, Lou. Yep. For this one, let's see. Yep, that's right. Yes, beautiful. That's actually beautiful. Yeah, quite beautiful. Remember my little comment at the beginning,
Oh,
right?
I also think that's addressed on that.
Ravina, he's the teacher. Would he ever do anything to hurt you?
Whenever a professor says something is easy or beautiful, bake it with like a whole can of salt.
Jeez.
Wow. Yeah, that is.
I guess I know what not to say around you.
So you just plug in that definition for the curve, just right there, and then times the derivative. This is gamma prime dt. It's set up beautifully for the w's to cancel. Get this. R I E to the I T. Good shit going down. Cancel, cancel. I had to find like some teaching demo recordings for Dr. Patnott, who's doing my evaluation. And I had to find one where I didn't drop an F-bomb.
Oh, God.
Did that take a minute?
That took quite a while.
Uh-huh.
And then another also where I didn't drop an F-bomb and where I didn't deliberately flaunt what I should be doing and saying I'm not doing what I should be doing.
On the same video.
On the same, yes, so I had to find
Wow.
one video where I was not doing either of those things. It was tough. I think there's one recently where that didn't happen. So the R's cancel as well, and we just get 2 pi I.
Wow.
Why didn't we have this in Calc 1, right? So what is this curve actually? Like geometrically, what is the sentence, the English sentence that describes it?
Is it in a line? A horizontal line?
It is not a line. Oh, well,
'Cause
it's
you-
not a line.
It's a climb.
It's a what?
Climb.
A climb.
Yeah.
It's not a climb either. What the hell
It's a climb.
I guess it's a complex line, is that what you're saying?
No, it's a climb is a circle or a line.
Oh, I like that.
Yeah, Mobius geometry, you can't tell the difference.
Got it. Okay, awesome. It's a climb, sure. Yeah. It's a circle centered where? W of radius R. Indeed. So notice that W, totally arbitrary. R, totally arbitrary. Here's W. Here's our circle. No matter what the radius is, the integral's the same value, 2 pi. Now notice that the thing up here is really badly behaved at W, at the center of the circle. We have division by 0 at the center. It's gonna turn out that when infinity pops into an integral, it leaves a residue. So in complex analysis, when we're integrating around closed curves, the only thing that can make it have value, and we'll get into this, I'm just saying this to give you like a sense of it. The only thing that can give a complex integral value is infinity. That's gonna turn out to be the case for us. Especially infinity showing up in just the right spot. So one of the questions I had asked, let's do this one together. I had also said, well, try this one. If you're done with that one, let's do this one together. So this is going to be integral 0 to 2 pi. I plug in the parameterization. So this is W plus ERE to the IT minus W, and that's all going to be squared. And then I've got times RIE to the IT. That's my gamma prime. And I simplify. So this turns into integral 0 to 2 pi, 1 over the W's cancel, and I'm left with R squared E to the 2IT on the bottom. And then here I've got RE to the IT. Oh, whoa, that's pretty exciting. RIE to the IT. Got some canceling going on. And I got like a big old 1 over R that's out in front, net effect of that. I've also got an I that comes out in front from there. And then when I subtract these, this is just e to the negative IT dt. Let's do calc 1. So this is I over R. This goes to e to the negative IT divided by the negative I. And then that's 0 to 2 pi on the t. The i's cancel. I work it all through. What do I get?
1 over negative R e to the IT.
Yes, and then when I plug in the limits, what do I get?
0.
Yep.
Pause.
I will pause. So this has still got like some division by 0 possibilities, right? Kind of like, this thing is bad at W, for sure. And we're integrating around a circle where that thing blows up, but the integrand is squared now, and somehow we're scot-free. Things came up clean. That's weird. Let's do something a little less weird.
Oh, slow down, dog.
Okay,
Slow down.
My God,
Not in a race.
it's not a race.
No, let him erase.
Let him erase. Yes, I will just, and it's not a race, and I'm going to erase.
Yeah.
Yes, ma'am. Going
Where
very
does
slow.
that negative I come from?
This guy here, this was when I took the antiderivative,
Okay.
just
So-
divided by that.
No, I was
Yeah.
still thinking it's
Does that make sense now?
Yeah.
Cool. Good question. I'm gonna start writing a problem, not gonna say any words, just gonna write some shit.
You can say some words now.
Okay, can I say some words?
I'm better now.
Oh, I'm glad to hear that. That's good news, Sydney.
Just have to get all my I's and T's in the right.
You gotta get them all. You've got to get them all. What if I have a weird ass curve? Like this one here. So this curve goes from 0 to 1, and then from 1 to I, and then from I to 0, and let's say it's oriented like that. So I've got this guy. What if I ask you to do an integral of just z on this curve C dz? Looks simple, right? This is like nice. This is like pretty chill. I'm asking to just integrate around something that is piecewise smooth. This is a piecewise smooth curve. So the thing we're going to do is step 1, parameterize C. And let's do that together. So let's do step 1 together. Create a parameterization for C, please. And we did start, this is why we practiced it, because now we get to use that. Sydney, is it cool if I erase the left side there?
Yeah, go crazy.
Okay, thank you. Just got a little PTSD from that encounter we had earlier.
Encounter.
Yes, that hostile encounter, terrifying. You were pretty out of control. I mean, I don't know.
You know what? I just needed a minute to write down all the words and the I's and the T's that you wrote down,
I got it.
and you were zooming.
You know those like?
And then my socks.
No, those shoes. Those like.
Birkenstocks.
Those all plastic?
You're like,
Wow, those are cool. They're like Croc-in stocks.
I love these. I have 2 pairs of these.
Nice. Are they actually Birks? They're Birk
Yeah.
brand? Cool. They look super comfy.
5 out of 5 stars. Would recommend.
I do not like wearing stuff that has this shadow. The cold feet inside the shoe. Because if I'm walking out all day, it's so funny.
I shuffle
know.
when I walk.
I was like, I'm pretty sure you're wearing shoes right now.
I
can't
hate
feel
wearing
when I
these
walk,
shoes
so
I'm
my feet
wearing.
Naturally slide back into my shoes because I walk on the shoes.
How many pairs of shoes do you all have at like any given time?
Ooh.
Oh.
Like right now in my room, I have like 7.
I haven't totally.
No, same.
That's a lot.
Well, it's
Hey, we are girls. We have to match our shoes up now.
I have like 7 or 8
Get
in my
black
room
shoes.
right now, but I wear probably 2 or 3 of them consistently.
Yeah.
I have.
That sounds like what I got.
Yeah.
Or 2 pairs of sneakers that are both run down and a pair of cowboy boots. That's it.
Cowboy boots?
Yeah, have you not seen me?
If
You
you
not
wear
seen
them,
these cowboy
I-
boots?
I don't think I've ever seen you not wear shorts.
From the D&D club.
I can
Okay.
confirm. I can confirm. I have seen Noah in jeans
Yeah,
Damn.
like twice.
full cowboy garb.
Yeah.
Full cowboy there. That's
yeah,
awesome.
remember last semester I was interning at a rodeo?
And so he had.
Oh.
I do now. Yes.
Yeah,
Wow.
so
It really just changed it, just like changed your whole lifestyle.
well, I got tickets. I had free tickets, and I was like, Hugo, you want them? Because they're too small for my family, so we're paying for ours. And then he didn't take them, and so to get back at him, I still wear the cowboy outfit every day, every D&D club. So,
That's awesome. What's your
Yeah.
character?
oh, my character is not a cowboy.
Not a cowboy.
No, it's
Not
just
like a cowboy wizard. or
no.
something.
It'd be funny.
That would be awesome.
Maybe next time.
I like the sound of that. So I think, let's see here. So this is the trick, right? Getting that guy there. I just did this for low hanging fruit. Like literally just move across 0 to 1. That's pretty easy for this piece here. And then we start at 1 and we end at I. So remember how I gave you some like formulas for this? But there's actually a couple ways to do this. Let's see, so I want this, these are my out, and I want, when t is 1, these are my ins. When t is 1, I want my out to be 1. When t is 2, and this is totally arbitrary, I want this to be my out here, because this is going to be my next segment of the line. So, how could we do this? Well, we could use point slope form for a line. Let's do that. So point slope form for a line is where we've got y minus the y coordinate equals, no, fuck, what am I doing? No, that's not gonna work. Well, let's see here. So I think here I want 2 minus t, so that when t is 1, I'm here. But I also want this dead when t is 1, so here t minus 1. I'm just kind of winging it, honestly.
Yeah, that's what I got.
Is that what you got? I think that works. The good news is you just need to put some kind of linear t expressions here and make sure that when t is 1, you're here. When t is 2, you're here. And that totally works out. So I'm going to use this parameterization. In fact, I'm going to actually clean it up. Sometimes leaving them this way makes more work. So this is 2 minus t plus it minus I. And so if I group this together in the classic form for a line, it's going to be negative 1 plus I times t plus 2 minus I. So then you do, if you pull this out, people think you're like mystically powered, right? Because it's like, this is your equation of that line. How did you get that? Yeah, it's kind of hacked it together. So I'm going to put this here, negative 1 plus I, and then plus 2 minus I. And how about that last one? So from 2 to 3, I just want to drop from I to 0. Any suggestions on how we can do that here?
Negative it plus 3i.
Let's check that out. So when t is 2, we're at positive I. When t is 3, that's beautiful. Looks great, Luke, thank you. So, to do this integral, I'm going to break this apart. I'm going to call this C1, C2, and C3. And this integral then becomes integral of z over C1 plus integral over C2 plus integral over C3. And we just have to do each of these now as we already know how to do. So let's just do this together and see what we get. Notice that gamma is going to change on each of those intervals, right? And so gamma prime will as well. There's a question.
Isn't that first proof from 0 to 1?
Thank you, Lou. Yep. Got it. Thank goodness. That's actually a lot better. I appreciate that. Thanks for catching that. Yes. And then Z here. So Z here becomes. Where's my T on that thing? I did just drop it. plus 2 minus I. And then the derivative of that is just negative 1 plus I. And that's gamma prime. This is gamma dt plus, now don't get too crazy here. I don't think we're gonna actually suffer this all the way through. But I just wanted to talk about how to set it up. Gamma 2 to 3, negative 1 to 3. And the derivative of this is just negative I dt. And I can already tell you what the answer is gonna be. What do you think the answer is? That's a good guess. Yep. Good guess, and that's the truth. But it's a painful road to get there down the formulas we've created for ourselves. Does anybody need? I'm not talking to anyone who doesn't need homework, so we don't need to have any emotional reactions to this. Does anyone need some problems to do on this stuff?
I wouldn't mind getting started.
Okay, cool. I'll hook you up. Yeah? All right. Okay. I'll come up with an assignment, post it on World Class, and email you. Sound good? Cool. That's it for today. I'll hang out and answer questions. Who's coming to math club?
Cookies.
Cookies. I made cookies. Yes. I made
They
cookies.
look like this, so I have to like.